On October 29th, 2025, the Sun did something it was never supposed to do. In less than 9 minutes, 3 full coronal mass ejections erupted in sequence, each one carrying billions of tons of charged plasma, each one moving at over 2 million kilometers per hour. They weren't random. Their trajectories converged toward a single corridor of space, and in that corridor, something was waiting. The interstellar object known as 3I-ATLAS, a visitor from beyond our solar system, had just reached perihelion, the moment of closest contact with the Sun. It should have disintegrated on impact. Every model, every simulation, every law of thermal physics said the same thing. No object of its size could survive that much radiation, but 3I-ATLAS didn't vaporize. It did something far stranger. As the solar plasma struck, its surface brightened, not white, not red, but electric blue. The emission lines sharpened. The brightness rose by more than 2,000%, and while the Sun unleashed enough energy to rip asteroids apart, the object held its course with perfect stability. No fragments, no recoil, no measurable deviation from its hyperbolic path. For 38 minutes, 3I-ATLAS endured what should have been annihilation, and when it emerged from the storm, it wasn't dimmer. It was alive with light, glowing in wavelengths that no natural comet has ever produced, bluer, in fact, than the Sun itself. Astronomers across 3 observatories, SOHO, Stereo A, and GOES 19, all captured the same impossible thing: a small, unbound body taking 3 direct hits from solar plasma and remaining untouched. What happened in those minutes has already begun to reshape how we think about energy, material, and the limits of survival in space. Because what was supposed to be a routine perihelion became a cosmic contradiction, a point where the known laws of thermodynamics seemed to fold in on themselves. And somewhere inside that contradiction, a new question was born. Did 3I-ATLAS merely survive the Sun, or did it use it? This is the 3I-ATLAS channel, calm, focused, and based on real-time solar system data. If you want to be part of this mission, hit subscribe right now. Comment ATLAS below to enter the giveaway for our exclusive 3I-ATLAS hoodie. Tell me where you're watching from and the exact time it is. You're now part of a global community tracking something the textbooks never prepared us for. Stay until the end. Because by the time you reach the final chapter, you'll understand why this single event, silent, brief, and almost ignored, might become the most important observation of the decade. Now, let's begin. At exactly 13:42, Universal Time on October 29th, 2025, the interstellar object known as 3I-ATLAS reached the point every astronomer had been waiting for: perihelion, the closest pass to the Sun. For weeks, observatories across the planet had been preparing for this instant. Most expected a brief, predictable flare as the object's frozen gases boiled away. But when the data arrived, what they saw was not gradual, it was instant. Every active observatory from the Stereo, Emission to SOHO, and GOES 19 reported the same thing at the same time. The brightness curve did not rise smoothly. It shot upward like a wall of light. Perihelion is normally a comet's most violent phase. When a body of ice and dust rushes into the inner solar system, sunlight warms its crust. Trapped gases escape, producing a glowing cloud called a coma. The pattern is familiar. Energy in, vapor out, brightness up. The math works every time. But 3I-ATLAS ignored the math. The increase in luminosity was extreme, greater than 100-fold within minutes. No comet in recorded history has brightened so quickly without visible fragmentation. No dust jets, no debris fields, no sign of rupture. The glow appeared uniform, stable, and blindingly blue. In physics, brightness follows a distance law. As a comet moves closer to the Sun, its activity grows according to a predictable curve. For ordinary comets, that curve steepens by a factor of 3 or 4. For 3I-ATLAS, the value was measured near negative 7.5. In plain terms, it grew almost 200 times brighter every time its distance from the Sun was cut in half. That is not sublimation. That is something else. To scientists, such a reading means one of two things. Either the instruments failed, or an entirely new energy process occurred. Calibration checks soon ruled out instrument error. 3 independent spacecraft, built by different agencies and positioned in different orbits, cannot all malfunction in the same way at the same moment. Then came the colour analysis. The recorded light was not white or yellow like reflected sunlight. It was blue, measurably, consistently blue. To emit that shade, a material would need to reach temperatures beyond the visible surface of the sun. Yet this object was small, dark, and cold before the encounter. Reflection alone cannot explain such a spectrum. The evidence points to emission, light being produced from within the material itself. As 3I-ATLAS swung behind the solar disk, moving at nearly 89 kilometers per second, it endured a blast of radiation strong enough to liquefy iron. Yet its orbit showed no deviation. Its spin remained constant. There was no visible shedding of mass. It passed through the storm untouched. Astronomers call it the perfect contradiction, a fragment from another star system surviving the most hostile environment known to nature. If it were an ordinary comet, it should have disintegrated long before its closest pass. If it were a rocky asteroid, it should have cracked under thermal stress. But it did neither. The moment of perihelion lasted less than an hour, yet its consequences will last for decades. It reminded scientists that interstellar visitors do not follow our rules. They arrive carrying chemistry and structure forged under conditions we can only imagine. What 3I-ATLAS revealed that day was not just resistance to heat, but a deeper mystery, an object that brightened beyond prediction, bluer than the sun and completely stable. It entered the light and came out unchanged. In that instant, the universe whispered a simple truth. We still do not know what matter is capable of when it comes from beyond the stars. Before it ever touched sunlight, before its name appeared in a single astronomy report, 3I-ATLAS was already different. The first hint came from its path. The numbers describing its motion did not curve into an ellipse, as planets and comets do. They opened outward, forever escaping. The trajectory was hyperbolic. That single word told scientists something profound. This object was not born here, it was passing through. To understand the importance of that shape, imagine drawing the orbit of a planet around the sun. It forms a neat oval, a closed loop. Energy is conserved, and the body returns again and again. A hyperbola is the opposite. It is open, unbound. Any object following it has more energy than the sun can hold. Once it enters the solar system, it will never come back. 3I-ATLAS was one of those wanderers, a fragment of material that had drifted between stars for perhaps millions of years before gravity finally pulled it into our neighbourhood. When astronomers first plotted its speed, they were stunned. At over 89 kilometers per second near perihelion, it was travelling too fast for any gravitational slingshot within our system to explain. Even Jupiter, the giant planet that hurls comets outward like stones, could not have given it that velocity. The only possible origin was interstellar space. That meant it carried chemistry, structure, and memory from another sun entirely. Its incoming angle was steep, slicing down through the plane of the planets like a blade. While ordinary comets drift in the same general direction as Earth, this one came from a path tilted more than 40 degrees off the ecliptic. It did not belong to the orderly family of solar debris. It was a stranger cutting through the crowd. The brightness was faint at first, a slow shimmer against the background stars. Ground telescopes captured it as a tiny point, no different from 1,000 others. But the movement gave it away. Night after night, its position shifted faster than any nearby asteroid. Automated tracking systems flagged the anomaly, and within days orbital data confirmed what the curve implied, an eccentricity greater than 1. That value, simple yet absolute, meant freedom. Once its nature became clear, the world's observatories turned toward it. The fascination was not just scientific but existential. Every hyperbolic visitor offers a direct sample from another star's workshop. It carries isotopes, ices, and metals that formed under alien conditions. For planetary scientists, it is like catching a messenger from beyond the local bubble. For physicists, it is a chance to test whether the laws we know apply universally or bend under different cosmic histories. Unlike its predecessors, the elongated Oumuamua and the icy Borisov, 3I-ATLAS, seemed to combine the behaviour of both. It reflected light like a solid rock, yet developed a coma like a comet. That dual nature blurred every boundary and classification. Was it a frozen shard or a carbon-rich core? A relic of another solar system's outer cloud or the broken surface of something larger and artificial? The hyperbolic path ensured we would never touch it to find out. As it approached the inner system, simulations traced its origin back toward the region of Lyra, though the uncertainties spanned light years. It might have been ejected from a dying planetary disk long before Earth even formed. It could have wandered in silence for eons, its surface scarred by radiation, its core still locked in the chemistry of another age. By the time it neared the Sun, it had travelled farther than any artifact humans have ever made. It was not visiting us out of intention, but by coincidence, drawn here by geometry alone. Yet in that geometry lay wonder. A single curve on a chart proved that our solar system is not isolated. Space is not empty, but filled with travellers, each bearing the story of a different origin. 3I-ATLAS was one of them, a hyperbolic stranger crossing our light for a brief moment before vanishing forever into the dark. When astronomers describe a comet's behaviour near the Sun, they usually talk in curves. The increase in brightness follows a clean mathematical relationship, a steady, predictable rise as sunlight heats the nucleus and vapour escapes into space. For decades, those curves have obeyed the same physics. The closer a comet gets, the brighter it glows, but within limits that the human mind can grasp. Then came 3I-ATLAS, and that understanding broke. In the hours surrounding its closest solar pass, the data showed something that did not fit any known model. Instead of a gentle slope upward, the luminosity spiked like a cliff. In technical terms, its brightening followed a power law near -7.5. To most people, that number means little, but to an astronomer it signals something close to impossible. For normal comets, the number hovers between -3 and -5. Even during violent outbursts or fragmentation events, it rarely exceeds -6. 3I-ATLAS exceeded them all. The first reaction from mission teams was disbelief, perhaps an error in calibration, perhaps an artifact caused by the intense glare of the solar corona. But independent instruments confirmed it one after another. Stereo A, SOHO, and GOES 19 each recorded the same steep acceleration in brightness. The data matched to within margins too small to dismiss as coincidence. Whatever was happening to the interstellar object was real, and it was happening fast. To understand why this was so strange, you have to imagine what a power law represents. It is a way of expressing how one quantity changes as another does. In this case, brightness versus distance. A slope of -4, the common comet value, means that as a comet's distance from the sun halves, its brightness increases 16-fold. A slope of -7.5 means the same distance change multiplies brightness by more than 180 times. That is not an ordinary acceleration, it is runaway behaviour. For this to occur naturally, something inside the object would have to release energy exponentially as it heated, as if each degree of temperature rise triggered an avalanche of reactions beneath the surface. Yet there was no sign of fragmentation, no sudden tail expansion, no debris cloud. The light grew stronger, but the structure held. That combination, violent luminosity with mechanical stability, defies the expectations of thermal physics. Some scientists propose the idea of buried supervolatiles, materials like carbon monoxide or carbon dioxide trapped under layers of dust. These substances vaporize at much lower temperatures than water ice, and could, in theory, erupt violently once exposed. But the curve of 3I-ATLAS was too steep even for that explanation. Volatile release tends to flare briefly and then stabilize as the pressure equalizes. Here, the brightening persisted over hours. Others speculated about a chain reaction on a microscopic level, perhaps grains of dust becoming electrically charged under intense solar radiation, discharging energy in waves through the coma. This would create pulses of light without requiring structural collapse. Yet even that scenario struggles to reproduce the continuous, smooth ascent captured by the coronagraphs. When the light curve from all three spacecraft was plotted on the same graph, the line was nearly vertical. No smoothing, no oscillations, just a single, relentless rise to a plateau of blinding intensity. In the language of data analysis, it was called a saturation event, but nothing in the sensors saturated, the signal itself did. The universe had for a moment turned up the brightness beyond what our equations allow. A few observers compared it to what would happen if the object itself were emitting, not reflecting. If sunlight were being absorbed and re-radiated as visible energy through some unknown process, the energy curve would climb this sharply. It would mean 3I-ATLAS was not merely reacting to solar heat, but actively transforming it into coherent light, almost like a natural amplifier. As the object rounded the far side of the Sun, the brightness finally levelled, but it never returned to pre-perihelion values. It stayed luminous, stable, and distinctly blue. The impossible curve had not been a momentary glitch. It marked a real transformation. For astronomers, this single measurement became a challenge to the foundation of cometary science. If one interstellar body could break the rule of 4 and sustain a slope of negative 7.5, then the assumptions about energy transfer, sublimation, and surface composition might all need revision. It was no longer a matter of why it brightened, but how reality allowed it. The numbers will be studied for years, tested, debated, recalibrated, and reanalyzed. Yet even if later models soften the slope, the memory of that near-vertical curve will remain. It was the moment when a visitor from another star reached into the predictable rhythm of the solar system and drew a line straight up. The impossible brightening curve that made scientists question whether light itself can be more than reflection, more than heat, perhaps even a message written in physics we have not yet learned to read. When the first colour data from 3I-ATLAS arrived, most analysts thought they were looking at an error. The numbers placed the object's light output in a range bluer than the Sun itself, an outcome so rare that even typing it into a database felt wrong. Comets are usually reddish or white, their dust scattering sunlight evenly or absorbing more of the shorter wavelengths. But 3I-ATLAS was different. Its spectrum leaned into the blue, a sign of energy release that no natural comet should display at this scale. Colour in astronomy is more than appearance. It is a fingerprint of process. The Sun's visible light peaks around the yellow-green region, where its temperature radiates most efficiently. When a comet reflects sunlight, its colour matches that of the Sun, sometimes reddened by dust. To measure bluer than the solar spectrum means the object is emitting more short-wavelength light than it receives. In other words, it is creating energy, not merely reflecting it. That is what caught everyone's attention. The phenomenon was confirmed across 3 independent platforms: Stereo A, SOHO, and GOES 19. Each satellite used different sensors and filters, yet each recorded the same shift toward the blue end of the spectrum. The colour index was not marginal or within error. It was statistically solid, several sigma above normal. There was no ambiguity left once the data were cross-referenced. Whatever 3I-ATLAS was doing near perihelion, it involved light emission that behaved as if the object were hotter than the Sun. The idea of bluer than the Sun seems poetic, but physically it means extreme excitation. Short wavelengths correspond to higher energy photons. For a small object to generate that light, it must either reach extraordinary temperatures or use a mechanism that channels energy directly into high-frequency emission. Both options are difficult to reconcile with the known physics of comets. The first natural explanation invoked known molecular bands. Cyanogen and diatomic carbon can glow green or blue when stimulated by ultraviolet light. Comets often appear slightly green because of these gases, but in those cases the effect is confined to the inner coma, a small region close to the nucleus. 3I-ATLAS displayed blue emission across an area roughly 300,000 kilometers wide, 25 times the size of Earth. That scale cannot be achieved by normal gas fluorescence. The energy requirement would be astronomical. Another hypothesis pointed to Rayleigh scattering, the same process that makes Earth's sky blue. If the coma were filled with ultrafine dust particles smaller than the wavelength of visible light, they would scatter blue light more effectively than red. The problem is that cometary dust is typically much larger. Submicron grains cannot survive long near the Sun's heat without evaporating. Even if they did, they would not produce the intensity measured. A more radical line of thought proposed plasma emission. When high-energy electrons from the solar wind strike molecules, they can knock them into excited states that radiate visible light. This process is known to occur around planets like Venus and comets in smaller amounts, creating faint auroras. If 3I-ATLAS carried a magnetic field or conductive material, it might have acted like a plasma antenna, converting charged particle energy into visible emission. That could explain both the blue colour and the sustained brightness without the usual dust production. Yet it would also require densities and field strengths far beyond what has ever been observed in natural cometary plasma. The final, most uncomfortable interpretation involved material properties. If the surface contained compounds capable of photoluminescence, substances that absorb ultraviolet light and emit visible light, the object could appear blue even at moderate temperatures. Certain carbon-based structures such as polycyclic aromatic networks can do this. So can engineered coatings designed to radiate under specific energy inputs. No one dared suggest intent, but the comparison was hard to ignore. The glow looked like activation. To rule out instrumentation error, engineers examined every stage of data collection. They checked for vignetting, stray light, and detector bias. None could produce the consistent cross-platform blue shift seen in all datasets. Each system's calibration files were decades deep, refined through countless solar observations. For all three instruments to misread in the same direction would require a near impossible alignment of flaws. By early November, teams agreed that the colour was real. The debate shifted from did it happen to how could it happen. If the blue light was produced by natural chemistry, then we were seeing physics pushed to its limits. If it was produced by plasma or structural fluorescence, it meant 3I-ATLAS was interacting with the sun in ways no natural object had before. Either way, the result was profound. In a universe where colour equals temperature, 3I-ATLAS had outshone its host star in energy per photon, if only for a few hours. It turned the familiar yellow glow of the sun into a backdrop for something colder, yet more radiant. A reminder that sometimes the strangest colour in the sky is not an illusion, but a new form of light we have never seen before, the blue shift that should not exist. When the first processed frames from the GOES-19 satellite appeared on the monitors, the image analysts thought they were looking at a lens flare. The bright ring surrounding 3I-ATLAS seemed too wide, too symmetrical, and far too luminous to belong to a small interstellar body. But the measurements were real. Around the nucleus of the object glowed an immense self-luminous envelope stretching roughly 300,000 kilometers across. That is 25 times the diameter of Earth, a scale more fitting for a gas giant's magnetosphere than for a transient comet. Comets usually carry a faint halo called a coma, produced when sunlight vaporizes surface ice into gas. That gas reflects sunlight and when illuminated gives the classic soft glow around the nucleus. The brightness fades with distance, and the colour is neutral or slightly green depending on the molecules involved, but the envelope of 3I-ATLAS broke every rule. It was not only brighter than expected, it appeared to emit its own light, radiating outward in visible wavelengths that did not match the solar spectrum. 3 separate instruments confirmed the finding. The stereo. A spacecraft captured the broad halo in its coronal camera. SOHO's LASCO imager recorded the same extension, and GOES-19 provided the most detailed temporal record. Across hundreds of consecutive frames, the luminous sphere held steady, expanding only slightly as the object rounded the sun. The brightness remained constant even as the geometry changed. This was not a passing reflection or a transient flare. It was a sustained phenomenon, a massive glowing cocoon following a visitor from beyond the stars. To grasp the magnitude of this envelope, imagine Earth placed at its centre. The glow would engulf our planet and still extend hundreds of thousands of kilometres into space. Within that volume, the density of particles must have been extremely low, yet somehow those sparse particles produced enough radiative power to compete with the sun's own reflected light. That balance defies common thermodynamics. In any normal coma, luminosity fades as the gas disperses. Here, the outer edge stayed nearly as bright as the core. One explanation considered by the photometry teams was that the light came from resonance fluorescence, molecules absorbing ultraviolet radiation from the sun and re-emitting it as visible light. Carbon monoxide and carbon dioxide can behave this way, creating blue and green emissions. But even at maximum efficiency, the energy output from known molecular bands cannot sustain such a massive glowing field. The emission was too smooth, too continuous, lacking the flickering variations typical of molecular lines. Another possibility involved plasma. Near the sun, the solar wind is dense with charged particles. If 3I-ATLAS possessed a magnetic or conductive surface, it could have interacted with that wind to produce large-scale electric discharges. Plasma luminescence can create a spherical glow as electrons excite surrounding atoms, similar to a planetary aurora magnified thousands of times. In laboratory terms, it would resemble a natural fusion chamber. a halo where light comes not from heat but from electrons accelerated through magnetic loops. Yet again, no known comet has ever shown such behaviour. The colour of the envelope added another layer of mystery. Data showed a bias towards shorter wavelengths, the same deep blue recorded in the spectral readings. Blue light indicates high energy emission and small particle scattering. If this were a dust cloud, it would imply a uniform field of submicron particles perfectly distributed in a hollow sphere. Nature rarely constructs such symmetry. As the hours passed, the envelope did not collapse. It persisted, wrapping the nucleus like a translucent shell, even as 3I-ATLAS continued on its hyperbolic path. When plotted in motion, it seemed almost stationary while the nucleus travelled through its centre, as if the light itself had mass or inertia. That effect led some observers to wonder whether the envelope was more than illumination, perhaps a boundary layer where magnetic pressure and solar radiation met equilibrium. The term envelope of light soon replaced coma in mission logs, because no other word captured its behaviour. It was not a cloud, not a tail, and not a typical emission field. It was an entity in its own right, a glowing sphere that defied the decay expected from any transient material. By the time 3I-ATLAS passed behind the Sun, the envelope had expanded even further but retained its brightness. It faded only when the viewing angle placed it directly against the solar corona, where its light merged with the background. When the object reappeared days later, the sphere was gone, leaving only a narrow residual glow. What created it remains a question without a clear answer. Whether it was a natural plasma shell, an energy resonance unique to interstellar chemistry, or the optical signature of a material unlike anything yet catalogued, the effect was undeniable. In those few hours around perihelion, 3I-ATLAS carried a sphere of pure light larger than most planets, an envelope that surrounded a traveller from another world and left humanity with a reminder that even emptiness can shine when the universe decides to show us something new. For all the attention it commanded, the most extraordinary moment in the story of 3I-ATLAS happened when no human eye could see. On October 29, 2025, as it swept through perihelion, the object moved directly behind the Sun from Earth's perspective. To every ground-based telescope, it vanished into the blinding glare of daylight. The sky swallowed it whole. From our planet there was nothing to observe, no trace, no flicker, no shimmer. Yet while humanity was blinded, our machines in orbit were not. Solar conjunction is one of astronomy's great blind spots. Whenever an object passes near the Sun in the sky, its faint light is overwhelmed by the solar disk, and telescopes must wait for it to re-emerge. It is a pause written into the rhythm of observation, an enforced silence that can last days or weeks. But spacecraft positioned beyond Earth's atmosphere do not share our geometry. From their unique orbits, they can shade their sensors, block the Sun's direct light, and capture the faint regions of the corona beyond. That is how the secret of 3I-ATLAS came to light. While Earth-based astronomers could only calculate where the object should be, Stereo A, SOHO and GOES 19 were already recording what it was actually doing. Each of those satellites carries a coronagraph, an instrument that uses an occulting disk to hide the Sun's bright centre and reveal what lies just beyond. Originally designed to study solar flares and coronal mass ejections, these instruments occasionally capture comets as they skim past the Sun. Most of those encounters are brief and unsurprising. A tiny point brightens, elongates, and disappears. 3I-ATLAS refused to follow that script. During the hours when it was invisible to Earth, the object performed what scientists later called a luminous event. The coronagraphs watched as its brightness erupted far beyond the range of ordinary sublimation. The data came through in bursts of images, each more puzzling than the last. At first, mission controllers assumed the flare was solar in origin, perhaps a stray plasma arc crossing the field. But when they plotted the trajectory of the bright point, it matched the predicted path of 3I-ATLAS perfectly. The anomaly was not on the Sun. It was in front of it, racing through space just a few million kilometres from the star's surface. To imagine what the spacecraft saw, picture the Sun's corona as a faint ghostly halo surrounding a dark circle where the solar disk has been blocked out. Within that luminous mist, a single point suddenly grows in intensity, then expands into a sphere. The light deepens from white to electric blue. It radiates evenly in every direction. For nearly 40 minutes, it outshines every background feature. Then, just as quickly, it stabilizes and holds, steady, silent, defiant against the furnace it has just crossed. From the surface of Earth, no observer knew this was happening. Radio signals from the spacecraft were delayed by the same solar interference that hid the object. By the time the data reached ground stations, the event was already over. Teams at the European Space Operations Centre and the National Oceanic and Atmospheric Administration processed the frames hours later, realizing that they had witnessed something impossible in real time without knowing it. The irony was poetic. For centuries, humans have looked up at the sun as the symbol of illumination, the source of light that reveals all. Yet at the very moment the universe presented one of its most puzzling displays, that same light blinded us completely. The sun became both the stage and the curtain. Astronomers later reconstructed the geometry. As 3I-ATLAS moved along its hyperbolic path, the alignment between Earth, the sun, and the object reached its exact centre just minutes before the brightening peak. The interstellar visitor was effectively shielded from direct observation at the same instant it defied physical expectation. It was as if the cosmos wanted to hide the experiment from human eyes, allowing only our mechanical proxies to bear witness. That concealment added to the aura of mystery surrounding the event. Had the object flared visibly in the night sky, millions would have seen it, and the phenomenon might have entered popular culture as a celestial omen. Instead, it unfolded in secret, recorded quietly by sensors designed for another purpose. Only after the data were decoded did the full picture emerge: the glowing envelope, the blue spectrum, the impossible stability. Hidden behind the sun, 3I-ATLAS performed its act of defiance in silence. No telescope watched, no human saw, no photograph captured it in natural light. Yet the evidence is there, burned into the digital eyes of our spacecraft. Proof that something extraordinary occurred just beyond the reach of vision. For a few fleeting hours, an object from another star slipped into the one place in our sky that light itself forbids us to look, and there, unseen, it broke the rules. Every mystery in astronomy begins with geometry, the angles between the observer, the object, and the source of light. Without the right alignment, even the brightest phenomenon can hide in plain sight. The case of 3I-ATLAS was a perfect example. What made its discovery credible was not one image or one data stream, but the way three separate spacecraft, placed at vastly different points in space, all saw the same impossible thing at the same time. Their separation in space turned a single anomaly into a verified event. At the time of perihelion, Stereo A, SOHO, and GOES 19 occupied three different observational posts around the Sun-Earth system. Stereo A orbited far ahead of Earth along its path around the Sun, stationed roughly 100 million kilometres from us at the Lagrange 2 point. SOHO floated between Earth and the Sun at the Lagrange 1 point, a gravitational balancing zone that keeps it in continuous view of the solar disk. GOES 19, designed primarily for weather monitoring, sat much closer to Earth in geostationary orbit, but its small coronagraph pointed outward, just far enough to glimpse the same region of space. Together, they formed a triangle of observation, a geometric configuration that made independent confirmation possible. Each spacecraft carried different hardware. Stereo's heliospheric imager captured wide fields, ideal for tracking moving objects. SOHO's LASCO C3 instrument provided deep exposures with decades of calibration data, making it the standard reference for solar events. GOES 19's coronagraph had lower resolution but exceptionally high temporal cadence, recording images every few minutes instead of hours. When something appears in all three systems, the odds of error fall nearly to zero. When 3I-ATLAS flared during perihelion, those three instruments were looking from different lines of sight, separated by tens of millions of kilometres. If the blue flash or the rapid brightening had been caused by a reflection, an internal sensor ghost, or a transient solar arc, each spacecraft would have recorded a different geometry. The pattern would shift with viewpoint, changing position or timing, but it did not. Across all three datasets, the event began within the same 10-minute window, peaked at the same brightness ratio, and occupied the same relative coordinates to the Sun. Geometry ruled out coincidence. The triangulation also revealed distance. By measuring the slight parallax between the three vantage points, analysts confirmed that the luminous object was not a solar flare or coronal feature, but an independent body located exactly where orbital models predicted 3I-ATLAS would be. The match was precise to a fraction of a degree. The object was not a glitch in the instruments. It was real, moving, and following a hyperbolic trajectory through the inner solar system. This geometric cross-verification became the backbone of the official reports. Without it, skeptics could have dismissed the readings as artifacts of solar noise. With it, they had to accept that an interstellar object had genuinely brightened beyond theoretical limits. The different viewing angles even allowed researchers to estimate the size of the luminous envelope. By comparing apparent diameters from each perspective, they derived a true physical scale of about 300,000 kilometers, a figure later confirmed through direct photometry. Beyond the numbers, the geometry carried symbolic weight. It demonstrated how modern science relies on perspective, literally and philosophically. One observer can be fooled by glare, by bias, by assumption. Three observers, separated in space and method, can reveal the truth that hides in one dimension. That is the power of triangulation, not only in astronomy but in all scientific reasoning. In the days following the event, data from all three spacecraft were layered together into a single composite visualization. The results showed 3I-ATLAS moving gracefully through the field of the Sun's corona, its halo expanding while its core held steady. Each instrument's position produced a slightly different parallax, turning the once flat images into a three-dimensional reconstruction of motion. For the first time, humanity saw an interstellar object interacting with our star from multiple vantage points. A cosmic scene captured in stereo, literally and figuratively. That spatial arrangement became known among mission scientists as the triangle of proof. It was accidental yet perfect. No one had planned for all three observatories to align that way, but geometry had cooperated at the exact moment it mattered most. In the end, confirmation did not come from belief or assumption. It came from distance, from the way perspective turns doubt into certainty. Three silent spacecraft spread across millions of kilometers looked toward the same furnace and saw the same impossible glow. Their lines of sight converged on a single truth. 3I-ATLAS had done something extraordinary. Geometry, once again, had delivered reality from illusion. In astronomy, brightness is language. Every flash, every gradual rise, every fading tail is a sentence written in light, and reading it correctly reveals the physics of what we see. For most comets, brightness is a simple conversation. Sunlight hits ice, the ice sublimates into gas and dust, and that mixture reflects light back to our telescopes. The pattern follows predictable laws. When an object approaches the sun, it brightens smoothly. When it recedes, it fades. But the brightness of 3I-ATLAS refused to speak that familiar dialect. It shouted instead, in a tone we had never heard before. When the chronographs of Stereo A SOHO and GOES 19 tracked 3I-ATLAS near perihelion, their light curves revealed something deeply unsettling. The rise in intensity was not smooth but abrupt, not curved but vertical. To scientists, the difference between a slope and a wall is everything. A slope means gradual heating, sublimation, dust reflection, predictable chemistry. A wall means a runaway process, something that turns energy into luminosity faster than equilibrium allows. At first, the data were treated with caution. Instruments can exaggerate changes when a source moves across their fields of view, especially near the blinding light of the sun. Analysts checked the orientation of the spacecraft, the background models, and even the thermal state of the detectors themselves. But no instrumental cause could account for the numbers. When plotted as flux versus time, the curve was nearly exponential. Brightness increased by more than 100-fold in less than an hour, and then stabilized at that new plateau as if the object had reached a new internal state. Brightness is not just an indicator of reflection, it is a measure of energy flow. Light can come from scattering, where sunlight bounces off particles, or from emission, where atoms and molecules release photons because they have been excited by heat or electricity. The spectrum of 3I-ATLAS told us that the second process was dominant. The light contained excess energy in shorter wavelengths, blue and violet, meaning it was not merely reflected sunlight. Something was generating or transforming energy on site. To calculate what that means, researchers converted the observed brightness into radiant power. Even with conservative estimates, the object was emitting tens of billions of watts, enough to power a small nation, yet its size was smaller than a mountain. No known comet or asteroid has ever released that much visible light without disintegrating. Normally, such luminosity would mean violent outgassing, jets of gas propelling fragments into space. But the orbital path of 3I-ATLAS remained unchanged. There was no sign of recoil, no acceleration, no tail dispersion. The object brightened without losing mass. That contradiction led to a new question. Could brightness be telling us something about the composition of the material itself? If 3I-ATLAS contained compounds that fluoresced under ultraviolet radiation, it might convert solar energy into visible light efficiently, much like phosphors in modern LEDs. The process would create high apparent brightness without corresponding mass loss. This hypothesis fits the data, but stretches the limits of natural chemistry. Materials that perform such energy conversions are known in laboratories, but have never been observed in interstellar space. Brightness also reveals geometry. In most comets, the inner coma is brightest near the nucleus, then fades outward. The GOES-19 images showed a uniform glow across a vast region, almost like a solid shell of light. That uniformity means the emission wasn't localized, it was volumetric. The entire envelope was active at once. Either sunlight was being trapped and scattered within a dense cloud, or the whole region was energized in some plasma process, emitting from every point simultaneously. Both explanations are extraordinary. The way brightness behaves over time tells us how stable an event is. Transient flares tend to fade as material cools or disperses. 3I-ATLAS didn't fade. Even days later, when the object moved away from the sun, it maintained much of its luminous power. That persistence implies that whatever caused the flare wasn't a single outburst, but a sustained mechanism. A system that reached equilibrium at a higher energy state and held it there. For scientists, brightness is a code, but it is also a warning. When an object's luminosity defies the rules of thermodynamics, it means our assumptions about its structure are wrong. Either it hides materials that store and release energy in ways we have not seen before, or it operates under physical conditions we do not yet understand. What brightness tells us about 3I-ATLAS is both simple and profound. It behaves like a source, not a mirror. Its light is not a reflection of the sun, but a statement of its own. For a brief time near perihelion, this visitor from another star wrote its message in pure radiance, a reminder that brightness, in the language of the universe, means more than visibility. It means power, persistence, and the presence of something that refuses to stay silent in the face of the sun. When the first data packets from the perihelion event of 3I-ATLAS arrived at the Solar Data Network, the initial reaction was not excitement, but disbelief. The numbers simply did not fit. Every known cometary model, from classical sublimation curves to modern plasma interaction simulations, broke under the weight of what the instruments had seen. The light curve was too sharp, the emission too blue, the stability too perfect. The object had endured 3 consecutive coronal mass ejections, each carrying billions of tons of plasma, and emerged unscathed, still glowing, still moving in a perfect hyperbolic line. For the first time in years, the mathematics of solar-comet interaction failed completely. In normal circumstances, science thrives on anomalies. Small inconsistencies push theories forward, encouraging refinement rather than revolution. But 3I-ATLAS was not a small inconsistency. It was a full collapse of predictability. The fundamental laws that describe how matter should behave under solar radiation pressure, ablation, outgassing, acceleration, all pointed toward one outcome: destruction. Yet destruction never came. The first model to fall was the sublimation model. According to classical thermodynamics, any icy body passing within a few million kilometers of the sun's surface should boil away in minutes. Even highly refractory compounds, such as carbonaceous chondrites, cannot survive temperatures beyond 2000 degrees Celsius. But the infrared spectrum of 3I-ATLAS showed no sign of rapid heating. Its surface temperature plateaued well below the expected value, as if something were absorbing and re-radiating heat with unnatural efficiency. Some researchers called it thermal shielding, though no one could explain what mechanism would provide such protection. The next theory under scrutiny was photolytic disintegration. the process by which solar ultraviolet light breaks molecular bonds, turning solid ices into gas. The brightness of 3I-ATLAS suggested massive energy exchange, but none of the typical chemical byproducts appeared in its spectrum. There was no measurable rise in hydroxyl radicals, no spike in water vapour lines, no trace of the molecular signatures that mark ordinary comets in distress. In other words, it glowed like a dying star but behaved like a polished stone. Astrophysicists began turning to plasma physics for answers. Perhaps they suggested the glow was caused by electron impact excitation, where solar wind particles collide with the object's magnetic field, producing aurora-like emissions. This mechanism can create sustained light without mass loss, but it requires the presence of a strong intrinsic magnetic field, something never before detected in a small celestial body. Instruments on GOES 19 tried to measure magnetospheric activity, yet the readings returned flat. If a field existed, it was subtle or shielded. Another school of thought proposed that 3I-ATLAS was covered in a layer of ultra-dark carbon compounds, capable of transforming ultraviolet radiation into visible photons through photoluminescence. Laboratory analogues of such materials exist on Earth, used in energy conversion devices and light-emitting coatings. If 3I-ATLAS were made of similar structures, it could, in theory, shine brighter the more it was bombarded by solar energy. The problem is that such compounds are rare in natural formation and require atomic-level precision to remain stable under extreme heat. The odds of them forming spontaneously in interstellar space are astronomically low. Each hypothesis sparked its own counterarguments. The plasma scenario demanded magnetic coherence. The luminescence theory required impossible chemistry. The thermal shielding model contradicted the energy balance equations. Scientists found themselves in a loop of logic. Every answer invalidated another. Theories that had explained comets for centuries were suddenly fragile, like glass under pressure. The debate spread through the global astrophysics community. Some wanted to invoke purely statistical reasoning. Perhaps we were witnessing an improbable combination of natural effects, angle, composition, and timing, that only seemed miraculous because we had never seen it before. Others warned against dismissing the data so easily. If something genuinely new was happening, clinging to broken models would blind us to discovery. By mid-November, a phrase began circulating in the research logs: theories under stress. It appeared in internal memos, academic discussions, and even press notes. It summarized a collective realization that what 3I-ATLAS had done near the Sun was not impossible in the sense of magic, but impossible in the sense that our mathematics had not caught up yet. And that, perhaps, is the most important outcome. Every law in science is provisional, waiting for the universe to test its edges. 3I-ATLAS was one of those tests, a stress fracture in our understanding, a controlled demolition of assumptions. It forced physicists to confront an uncomfortable truth, that we may know the equations of heat and motion, but we still do not know the full vocabulary of light. In the end, the object gave us no answers, only contradictions. But those contradictions are the raw material of progress. 3I-ATLAS turned every confident model of cometary behaviour into a question mark and reminded humanity that the cosmos is not obligated to stay within the margins of our textbooks. When scientists began dissecting the spectral fingerprints from 3I-ATLAS, they were searching for something simple, a chemical explanation. Every comet, asteroid, or interstellar object carries a unique signature in light. The gases that surround it absorb and emit specific wavelengths, leaving patterns of lines that reveal what the object is made of. But what researchers found in the light of 3I-ATLAS was not simplicity, it was contradiction. The first step in any spectral analysis is subtraction. Scientists remove the background glow of the Sun, filter out the noise from solar plasma, and isolate the faint reflected and emitted light from the object itself. When that was done, three main bands stood out, one belonging to diatomic carbon, another to cyanogen, and a third faint pattern that did not match anything in the standard cometary catalogue. The presence of diatomic carbon and cyanogen was expected. Both are common in comets, responsible for the greenish hues often seen in their comas. But here, the ratios were off. The cyanogen band was far stronger than it should have been at such high temperatures, and the carbon signature was displaced, suggesting a level of excitation far beyond ordinary solar heating. In simple terms, the molecules around 3I-ATLAS were behaving as if they were inside a laboratory plasma chamber, not orbiting the Sun. The energy state implied collisions and electron transitions that required dense, magnetically confined environments. The corona of the Sun can provide such energy, but only for brief moments and only across vast distances. For that same intensity to be measured within the confined halo of a small interstellar object defied expectation. To double-check, teams at the European Space Agency and NASA compared readings from different instruments. SOHO's ultraviolet spectrometer saw the same anomalous bands that GOES 19's optical detectors had hinted at. Even the low-resolution sensors aboard Stereo-A detected a faint echo of the same pattern, confirming that it wasn't a sensor artifact. The molecules were real, but their state was strange. One possible explanation emerged: fluorescence. When molecules absorb high-energy ultraviolet light and then emit it at lower visible wavelengths, they can glow intensely without necessarily indicating high temperatures. This process could account for the overexcited cyanogen bands and the spectral shift in carbon. But fluorescence on this scale requires continuous pumping, a steady stream of energy input, such as constant bombardment by high-speed particles. That would imply that 3I-ATLAS was interacting with the solar wind in a way no other comet had before. Another, more radical interpretation suggested that the molecules were being replenished from within. If the object contained pressurized pockets of gas sealed beneath a non-porous crust, intense solar heating could release them in sudden bursts, creating waves of chemical emission. Yet no periodic spikes appeared in the data. The glow was smooth, stable, and evenly distributed. Whatever process was driving it was not explosive but balanced, sustained emission from a system in equilibrium. The third mystery band proved the most troubling. It appeared near the border between ultraviolet and visible light, in a region associated with metallic ions such as nickel and magnesium. However, the ratios were reversed. Normally, nickel is far less abundant than magnesium in cometary material. Here, nickel dominated. More bizarrely, the spectral lines suggested nickel without iron, an elemental pairing almost unheard of in natural bodies, since the two metals typically form together during stellar nucleosynthesis. The presence of nickel-rich, iron-poor compounds hinted at an origin that did not match any known planetary or interstellar formation model. This discovery reignited speculation that 3I-ATLAS might not be a traditional comet at all, but a fragment of an exotic body, perhaps the remnant of a disintegrated planet core, or even a material manufactured in an environment with controlled chemistry. Scientists were careful not to jump to conclusions, but the data refused to fit any comfortable category. Molecular analysis is supposed to bring clarity. It tells us temperature, pressure, and composition, the building blocks of identity. But in this case, it only deepened the mystery. The high ratio of cyanogen to carbon, the persistent blue emission, the nickel without iron, each piece of the puzzle contradicted the last. When combined, they painted a picture of material that reacts to energy not passively, but actively, as if designed to channel light rather than merely endure it. Months after the event, researchers continued to run laboratory simulations trying to reproduce the spectral lines. Some used carbon nanotube lattices, others experimented with ionized carbides and exotic alloys. None could match the exact wavelengths. The material of 3I-ATLAS remained unique. In the end, the molecules told us something profound, that chemistry alone could not explain this object. The clues were molecular, but the meaning was structural. Whatever 3I-ATLAS was made of, it was not built in the same workshop as the rest of our solar system. Its light carried the fingerprints of a different chemistry, one born under a different star, or perhaps under conditions that we have yet to imagine. When every conventional explanation failed to account for the blue radiance of 3I-ATLAS, scientists turned toward a different language, that of plasma physics. It was not a comfortable shift. Plasma, the fourth state of matter, is notoriously difficult to model. It behaves neither like gas nor solid, and its motion follows electromagnetic forces far more complex than gravity alone. Yet as the evidence accumulated, the plasma hypothesis became impossible to ignore. The first hints came from the brightness curve itself. The steady, sustained glow around 3I-ATLAS was inconsistent with thermal emission or chemical fluorescence. Instead of fading as the object cooled, the light remained constant even as it receded from the sun. That pattern suggested a self-sustaining interaction, something dynamic, powered by charged particles rather than passive reflection. The idea took shape quickly. What if 3I-ATLAS was not just reflecting sunlight but conducting energy from the solar wind? Near the Sun, space is not empty. It seethes with high-energy protons and electrons flowing outward at hundreds of kilometers per second. When this charged stream encounters a magnetic or conductive object, electric currents can form, creating glowing plasma sheaths, auroras on a cosmic scale. If 3I-ATLAS possessed even a weak magnetic field, it could trap and accelerate particles, turning the region around it into a radiant cocoon. That was the essence of the plasma hypothesis. The interstellar object was functioning like a natural plasma reactor. Supporting evidence appeared in the form of subtle oscillations in the light intensity captured by the high-speed cameras aboard GOES 19. Every few seconds, the brightness flickered in patterns too regular to be random. The frequency of those oscillations matched the predicted rate of Alphen waves, magnetic ripples that travel through plasma when charged particles oscillate along field lines. This suggested that the glowing envelope around 3I-ATLAS was not just light, it was a living electromagnetic environment, pulsing in resonance with the solar wind. For such a system to exist, two conditions had to be met. The object needed to conduct electricity, and it needed to maintain a stable magnetic geometry. The first could be explained if its surface contained metals or graphitic carbon, both excellent conductors. The second, however, was more puzzling. A comet-like body should have no internal dynamo, no molten core generating magnetism. Yet the field inferred from the plasma oscillations appeared organized, not chaotic. Either 3I-ATLAS retained magnetized material from its parent system, or it was coated in a ferromagnetic layer that preserved alignment across eons of interstellar travel. Researchers began comparing the event to known plasma interactions in our solar system. Jupiter's moon, Io, glows in ultraviolet light, because its volcanic surface ejects charged particles that feed into Jupiter's magnetosphere, producing electric currents along invisible lines of force. Venus exhibits faint plasma emissions when solar wind compresses its induced magnetic field. Both are examples of electrical coupling between a celestial body and the solar environment. 3I-ATLAS, however, appeared to magnify this effect beyond anything previously seen. Its entire envelope radiated visible light, and its power output dwarfed those planetary auroras by orders of magnitude. Simulations attempted to model how much energy the solar wind could realistically deposit into such a small target. Even under the most optimistic conditions, it was not enough. The glow of 3I-ATLAS required conversion efficiency approaching 30%, far higher than any natural plasma interaction ever measured. That figure left researchers uneasy. Nature is rarely so efficient. Skeptics countered that perhaps the object's shape or rotation amplified the effect. If it were elongated, spinning along its long axis, it could generate a fluctuating electric potential as it sliced through the solar wind. Each rotation might recharge the surrounding plasma, sustaining the glow like a strobe. The rotation rate of 3I-ATLAS remains unknown. The blinding light of perihelion obscured direct measurements, but the periodic flicker in luminosity hints that it might indeed have been rotating, feeding its own plasma cocoon in rhythm. As weeks passed, data from the Solar and Heliospheric Observatory confirmed that the blue hue of the emission corresponded to ionized carbon and oxygen, elements common in cometary dust but rare at such high excitation levels. That finding strengthened the plasma theory. The blue light was the visible signature of electrons recombining with stripped atoms, a process that releases precisely the wavelengths recorded by the instruments. By the end of the analysis, the plasma hypothesis stood as the most plausible and the most unsettling. It proposed that 3I-ATLAS had become, for a brief time, an artificial-like structure in nature, a body generating a self-contained electromagnetic field strong enough to deflect, trap, and convert solar energy into visible radiation. It was neither comet nor asteroid, but something in between, a solid object wearing a luminous skin of charged particles. Even so, the theory could not answer the most haunting question of all. How did an interstellar fragment acquire the perfect conditions to behave like a plasma engine? Was this a coincidence of composition and geometry, or evidence of design hidden in nature's complexity? For now, no one knows. But the plasma hypothesis at least gives the mystery a name, a framework where the impossible glow of 3I-ATLAS becomes a story not of broken laws, but of physics operating in its most electric, untamed form. When the final orbital measurements of 3I-ATLAS came in, they confirmed something that seemed quietly miraculous. Despite the enormous forces it had endured near the Sun, the heat, the radiation, and the direct impact of solar plasma, its path through space had not changed. No measurable deviation appeared in its trajectory. No acceleration, no slowdown, no spin alteration. In the language of celestial mechanics, it had experienced pressure without push. Every comet or asteroid that releases gas or dust under solar heating experiences a recoil effect. It is the same principle that allows rockets to move through vacuum. For every particle expelled, there is an equal and opposite reaction. This non-gravitational acceleration, however small, is always detectable. It nudges comets off their predicted courses by measurable fractions of a degree. When scientists saw the intensity of the outburst around 3I-ATLAS, the massive glowing envelope and its apparent radiation pressure, they fully expected to see such deviations. Yet the orbital data remained exact. Its hyperbolic path, calculated, weeks before perihelion, stayed perfect. At first, researchers suspected computational error. Perhaps the observational data were being smoothed by interference from the Sun's glare, hiding subtle shifts. But when triangulated from 3 spacecraft, Stereo A, SOHO, and GOES 19, the same conclusion emerged. Within observational limits, the object's motion remained gravitationally pure. It moved exactly as a passive body should, as though the vast energy radiating from it had no mechanical consequence. This finding contradicted the very foundation of Newtonian mechanics. Energy cannot appear without cost. If 3I-ATLAS was emitting billions of watts of light and interacting with the solar wind strongly enough to form a luminous plasma shell, then momentum must have been exchanged. Somewhere, somehow, that energy should have translated into movement. But it did not. The glow expanded, the corona shimmered, yet the nucleus sailed through space like an anchored beacon. Some physicists tried to explain the effect as a balance of forces. Perhaps the solar radiation pressure pushing inward was exactly countered by mass loss pushing outward. Others suggested that the apparent emission might be symmetric, energy radiating in all directions equally, cancelling its own thrust. In theory, a perfectly spherical outflow of photons and plasma could create immense brightness without acceleration. But natural processes rarely produce such symmetry. Real comets vent through fractures and jets, never in perfect balance. The sheer stability of 3I-ATLAS implied either extraordinary coincidence or underlying order. The plasma hypothesis provided another possible answer. If the object's luminous halo was not material outflow, but an electromagnetic field interaction, then no mass was actually leaving the surface. Instead, the glow would represent trapped particles spiraling within magnetic lines, producing light but not thrust. The body itself would remain inert, its mass unchanged. In this model, 3I-ATLAS would act more like an induction coil than a jet, a structure responding to solar energy without ejecting anything. That would explain why its orbit stayed true. It was not being pushed, it was resonating. Even within that framework, though, something still felt off. The Sun's own radiation pressure should have exerted at least a measurable drag. Yet calculations showed that the expected perturbation was lower than 1/10 of prediction. It was as if the object reflected or absorbed sunlight in a way that negated the usual momentum exchange. Some theorists speculated about photonic shielding, materials capable of re-emitting energy at equal and opposite angles, effectively nullifying the push of light. Such behaviour is known in metamaterials engineered on Earth, but never in nature. The anomaly also raised questions about inertia. Could the composition of 3I-ATLAS include extremely dense or exotic matter, giving it such overwhelming momentum that no external force could noticeably alter its path? That idea verged on speculative physics, bordering on the notion of interstellar relics composed of degenerate material, fragments of long-dead stars travelling among us. Yet the object's brightness contradicted that. Dense matter should not glow. Over time, the phrase pressure without push became shorthand among the observing teams, a poetic label for a physical impossibility. It described not just the absence of motion, but the quiet defiance of a body bathed in violence yet utterly unmoved by it. For scientists, it was a humbling reminder that force and motion, the oldest principles in physics, still hold corners of mystery. When future missions retraced the event, the orbital records of 3I-ATLAS stood uncorrected. The visitor's path through the solar system remained an unbroken arc, precisely matching the equations written before it met the Sun. In every sense measurable, it had felt no push at all, and so it continued outward, leaving behind a paradox written in the faint blue light that once surrounded it. Proof that the universe can apply immense pressure, yet still fail to move what was never meant to yield. In science, meaning often emerges not from what we see, but from what we compare. Every discovery gains its definition by standing next to another. When 3I-ATLAS blazed through the inner solar system, scientists reached instinctively for precedents, other visitors, other anomalies, other data points that could help make sense of the impossible, and there were only two that belonged in that rare category: Oumuamua in 2017 and 2I Borisov in 2019. Together, they formed the entire record of confirmed interstellar objects ever observed. But even among those few, 3I-ATLAS stood apart. The first of its kind, Oumuamua, had entered our system quietly. It showed no coma, no tail, and no glow, just a dim, elongated rock tumbling through space, faintly reflecting sunlight. It accelerated slightly as it left, a subtle drift that scientists could not explain through gravity alone. The acceleration was small but real, as if sunlight were somehow pushing on a surface that absorbed nothing. The debate that followed lasted years. Was it icy and venting invisible gas, or was it a fragment of light-sailing material from another world? The mystery remained unresolved, but its behaviour set a benchmark: non-gravitational motion without visible energy output. Then came 2I Borisov, the opposite in almost every way. It was a classic comet in appearance, trailing gas and dust in long arcs, disintegrating as it neared the Sun. Its composition was familiar: water ice, carbon monoxide, and other volatiles common in our own comets. It brightened and faded predictably. It was alien in origin but not in behaviour, a reassurance that the universe beyond our solar system followed the same rules. 3I-ATLAS destroyed that comfort, where Oumuamua accelerated without light. 3I-ATLAS radiated without motion. One defied mechanics, the other thermodynamics. Side by side they formed a mirrored pair of contradictions. Together they drew the boundaries of our ignorance. The comparison became the centerpiece of every late-night discussion among astronomers in October and November 2025. On paper, the differences looked clean. Oumuamua was a non-luminous drifter, Borisov a predictable evaporator, and 3I-ATLAS a self-luminous survivor. But the deeper scientists looked, the more entangled the parallels became. Both Oumuamua and 3I-ATLAS resisted disintegration near the Sun. Both behaved as if surface chemistry and internal energy storage operated under unfamiliar laws, and both left data that could be interpreted as electromagnetic interaction rather than chemical. The silence between them, the gap of years and the absence of intermediate examples, became a kind of question mark in the history of interstellar research. How could two consecutive visitors from deep space display such perfect opposites of impossible behaviour? Was there a continuum of objects between them that we simply had not detected? Or were these rare events glimpses of two entirely separate categories of matter, each shaped by environments unknown to human science? For Oumuamua, theories eventually leaned toward natural explanations stretched to their limits: hydrogen outgassing, fractal ice, or pancake-shaped geometry. For 3I-ATLAS, the same scientific caution struggled to hold. Its brightness increase was far too large, its spectrum too coherent. The comparison brought out a painful truth, that the scientific method depends on repetition, and the cosmos was refusing to provide it. There were no intermediate examples, no control experiments, no second chance. In the public imagination, the contrast between the two objects reignited the old speculation. What if interstellar space carried more than natural debris? What if some of these fragments were not accidental wanderers but artifacts, relics of cosmic engineering scattered through the galaxy? Scientists avoided the phrase, but it lingered between the lines of every conference summary. The symmetry was hard to ignore. One object without thrust that moved, another with radiant energy that stayed still. In their imbalance, they formed a single equation: motion without force versus energy without loss. Yet the true comparison, the silent one, was emotional. Oumuamua had left behind curiosity. 3I-ATLAS left behind discomfort. One whispered possibility, the other demanded explanation. They stood like bookends of the unknown, bracketing 8 years of observation with questions that reached far beyond their orbits. In quiet corners of research archives, some scientists began to label them not as anomalies, but as data boundaries, edges of known physics beyond which new rules might begin. If future observatories ever detect a fourth or fifth interstellar visitor, those comparisons will guide how we interpret it. Until then, the contrast remains. One faint and fleeing, one bright and defiant. The universe gave us 2 clues written in opposite languages, and between them lies silence, a silence that speaks louder than any signal we have yet received. Every great discovery in space science begins the same way, with disbelief. When the first images of 3I-ATLAS came through showing its unprecedented surge in brightness, the teams at Stereo A, Soho and GOES 19 did not assume they had just witnessed a physical miracle. They assumed their machines were wrong. In astronomy, 1,000 things can masquerade as anomalies: lens flares, cosmic rays, sensor saturation, or thermal drift. The first duty of any scientist is to doubt the instrument before doubting the universe. And so began what became known internally as the calibration crisis, an intense, week-long attempt to prove that the data were flawed. At first, the leading suspicion was simple saturation. When an object suddenly grows brighter than expected, its image sensor can overload, producing exaggerated or artificial light curves. Engineers checked the telemetry, exposure levels, pixel gain settings, dark current compensations. Everything was within normal range. The detectors had not saturated. Each spacecraft's auto-exposure algorithm had adapted in time to handle the sudden influx of light. The instruments had seen what they were built to see. Next came the hypothesis of solar contamination. Perhaps a coronal flare from the sun's limb had scattered light into the instrument optics, creating a false signal. Coronagraphs are notoriously sensitive to this effect, but when scientists compared the solar activity logs, they found nothing unusual. The nearest solar flare had occurred 3 hours earlier on the opposite hemisphere of the Sun. Moreover, the geometry between each spacecraft was different, yet the anomaly appeared at the same location relative to the Sun in all 3. Stray light could not synchronize across millions of kilometers. Then came the question of thermal noise. As spacecraft orbit near the Sun, internal temperatures fluctuate, sometimes distorting images. The team checked the onboard thermal sensors. All were stable. No rapid heating or cooling events occurred during the time of the flare. Data analysts began to worry. With each failed explanation, the evidence pointed closer to the unthinkable, that the instruments were fine, and the object itself was extraordinary. Yet scientists are trained to exhaust every mundane option before stepping into the unknown. So they began cross-referencing calibration files, pulling records from as far back as 2005, comparing baseline measurements of stellar light sources against the recent data. Each comparison confirmed that the sensors were operating within tolerance. At this point, the conversation shifted from instrument failure to interpretation failure. Maybe the instruments were accurate, but our assumptions about what they measured were incomplete. Could there be an optical illusion caused by polarization of the light? If 3I-ATLAS emitted highly polarized radiation, the sensors could exaggerate its brightness. But polarization requires structure, a preferred direction in the emitting field. For a tumbling comet-like body, that would require physical coherence across tens of kilometers. Still, polarization analysis found that the light was nearly isotropic, evenly distributed in all directions. When data scientists overlaid the 3 datasets from Stereo A, Soho, and GOES 19, the match was too precise to dismiss. The timestamps aligned down to the minute, and the intensity profiles were identical within 2%. Independent systems, independent clocks, independent optics, yet all told the same story. At that moment, a shift occurred. What began as a search for calibration error became an acknowledgement of something outside known behavior. If it's not the machines, one engineer wrote in an internal memo, then the problem is with physics. The phrase spread quietly among the mission teams. Still, there were skeptics. Some argued that the anomaly might be a catastrophic software error, perhaps a shared flaw in the image processing pipeline. To test this, raw telemetry was extracted from each satellite and reprocessed using independent algorithms at different labs across the world. The results were identical. The anomaly survived every filter, every model, every attempt to erase it. By the end of the review, the engineers had arrived at an unsettling consensus. The instruments had behaved perfectly. The calibration was sound. The readings, in all their impossibility, were real. The data described an interstellar object that had endured one of the most intense radiation environments in the solar system, emitted light beyond theoretical limits, and yet left its trajectory unchanged. Calibration had not failed. Catastrophe had. The catastrophe belonging to theory itself. The laws that once defined predictability had bent under pressure, revealing cracks too deep to ignore. 3I-ATLAS had turned the very tools designed to measure the universe into witnesses of its rebellion. In the quiet aftermath, as engineers archived the verified data, one scientist summed up the feeling in a single line of her report. "We built these instruments to reveal the sun. Instead, they revealed the limits of our certainty." When the blinding flare of 3I-ATLAS finally subsided and the data began to settle, a more fundamental question emerged. What was this object actually made of? Every comet ever studied shares a common recipe: frozen water, carbon dioxide, ammonia, dust, and stone. When sunlight strikes those elements, they vaporize, releasing gas and forming the luminous coma that makes comets so familiar. But 3I-ATLAS refused to follow that rulebook. It shone like molten metal, resisted vaporization, and emitted a blue hue that ordinary ice and dust cannot produce. Whatever it was composed of, it was not the fragile snowball astronomers expected. The first chemical clues came from spectroscopy, the same tool that had exposed the molecular oddities around the object. The reflected spectrum showed a flat response across the visible range, interrupted by faint absorption lines, where metals like magnesium and nickel absorb light. Normally, these lines are weak in comets, diluted by the dominance of volatile ices. Here they were sharp and clear, suggesting that the surface was not ice-coated at all, but metallic. Yet the temperature of the object near perihelion reached levels that should have liquefied any exposed metal. Still, it endured, smooth, bright, unbroken. That defiance of heat led some scientists to consider refractory materials, the kind that can survive in furnaces hotter than lava. Substances like tungsten, titanium carbide and silicon nitride can remain solid above 2000 degrees Celsius. Such compounds are rare in nature, but have been found in trace amounts inside certain meteorites, remnants of ancient supernovae. These minerals form under extreme pressure and temperature, far beyond the conditions of ordinary planetary birth. If 3I-ATLAS contained them, it might have been forged in the violent debris of a dying star, a relic of cosmic metallurgy drifting between systems. But even that theory had limits. The glow of 3I-ATLAS was too smooth, its light too uniform to come from a mixture of random minerals. Its albedo, the measure of reflectivity, was abnormally high, close to that of polished metal. It behaved not like rough rock, but like a mirror. Several scientists proposed that its surface might be coated in a thin layer of carbon allotropes, graphitic structures capable of absorbing ultraviolet light and re-emitting it in visible wavelengths. On Earth, similar effects are seen in engineered materials such as graphene composites and diamond-like films. These coatings can survive temperature swings and radiate absorbed energy as visible glow, producing efficiency levels that match the observed brightness of 3I-ATLAS. The problem was that such films do not form easily. They require slow cooling, low-pressure deposition, and time, the opposite of what violent stellar environments provide. For such a layer to exist on an interstellar object implied either an incredibly long natural polishing process or something more directed, something resembling design. No one wanted to use that word publicly, but the resemblance was difficult to ignore. Laboratories on Earth began attempting to reproduce the optical properties using carbon and metal composites under vacuum heating. The results were close, but not exact. The artificial samples lost brightness quickly as they oxidized or degraded, while 3I-ATLAS maintained its luminosity for days after perihelion. Some theorized that its surface might include exotic glassy materials infused with metallic nanoparticles, a self-healing reflective shell capable of radiating energy without erosion. Others speculated about alloys formed in supernova ejecta, structures unknown to terrestrial chemistry. The absence of dust emission was another clue. Normal comets shed material continuously as they heat. The coma of 3I-ATLAS, however, remained optically clean. It glowed, but it did not shed. That stability meant the surface was not sublimating. Whatever the material was, it was sealed, dense, and inert against radiation. Observers described it as an object that glows without bleeding. By November, discussions within the European Space Agency began referring to 3I-ATLAS as a refractory interstellar remnant, a term vague enough to avoid controversy, yet specific enough to acknowledge its strangeness. The phrase implied an object built of something closer to industrial ceramic than cosmic ice. And still, the mystery deepened. The light behaviour, the endurance under heat, the absence of acceleration, all pointed to a material engineered for stability, whether by nature or by chance. It was as though 3I-ATLAS had been sculpted to survive what no comet should. In the end, a question of material became a question of origin. What kind of world could produce an object so resistant to the sun itself? Was it forged in the heart of a supernova, crystallized in the debris of a dying star, or shaped in a place where matter is disciplined, not chaotic? Until another visitor like it arrives, no one can say. For now, the best we can do is acknowledge what the data demand, that in a universe of fragile dust and vapour, one traveller arrived made of something harder than heat, something that turned the fury of the sun into nothing more than reflected light. By early November, when all conventional explanations had been tested and discarded, a quiet unease began to ripple through the scientific community. The data on 3I-ATLAS had survived every attempt at refutation. The object had emitted vast energy without mass loss, maintained perfect trajectory despite solar pressure, and displayed material endurance far beyond any natural composition known to form in planetary systems. At some point, the discussion shifted from what it was to why it behaved that way. That shift gave birth to the most controversial idea of all, the engineered hypothesis. The notion began in back-channel messages, not press releases. In archived internal correspondence, one astrophysicist phrased it carefully. If an object behaves as if it were designed, the least we can do is test that possibility. It was not an argument for alien technology, but for intellectual honesty. If every natural explanation had failed, the hypothesis of intentional structure, however unlikely, needed to be examined on its physical merits. At its core, the engineered hypothesis did not suggest intelligence guiding the object through space. It proposed something subtler, that 3I-ATLAS might be the fragment of a constructed material, perhaps the debris of a system once capable of controlled energy manipulation. In this framework, its strange properties, the spectral uniformity, the heat resistance, the emission efficiency, were not mystical but the residual traits of an artifact built for endurance. The argument rested heavily on the object's surface behaviour. During perihelion, 3I-ATLAS should have boiled away in seconds. Instead, it transformed solar radiation into coherent blue light, with an efficiency approaching that of engineered photonic materials. On Earth, the only substances that come close are nanostructured films used in optical devices, surfaces designed to manipulate light at the quantum level. To find a natural body displaying similar optical precision on an interstellar scale stretched the limits of probability. Another piece of evidence was symmetry. The luminous envelope around 3I-ATLAS was nearly spherical, expanding evenly in all directions. Cometary comas are never so balanced. They follow the irregular venting patterns of their nuclei. Symmetry implies structural regulation, a geometry responding uniformly to external energy. To some researchers, that suggested that the object's composition might not be random rock and ice, but a continuous lattice, perhaps crystalline or metallic, that distributed energy evenly across its surface. Skeptics countered that nature often produces symmetry, snowflakes, bubbles, magnetic fields. But the defenders of the engineered hypothesis pointed out that those examples occur under equilibrium conditions, not amid the chaos of a solar encounter. The survival of 3I-ATLAS was an equilibrium under assault, a stability that refused to break. Speculation deepened when the third spectroscopic anomaly, nickel without iron, was re-examined. In natural stellar processes, those two metals are forged together. To separate them requires a process of selective refinement. The data implied purification, as if the material had been smelted or filtered. Such purity can emerge through rare astrophysical events, like the tidal disruption of the white dwarfs. But the coincidence of all these anomalies within one object strained statistical credibility. Some scientists turned to history for precedent. In 2017, a similar debate had surrounded Oumuamua. A handful of researchers had suggested that its shape and motion resembled a fragment of a light sail, a concept for interstellar travel proposed by human engineers. The idea was dismissed as speculative, but in retrospect many saw parallels. Oumuamua accelerated without visible propulsion. 3I-ATLAS radiated without motion. Both defied inertia in ways that mirrored deliberate design principles. Energy without waste, motion without loss. The hypothesis found no official endorsement, yet it refused to die. Research papers avoided direct language but lingered on its edges, describing photonic efficiency, material coherence, and engineered analogues. For the public it became a whispered fascination, the suggestion that somewhere in the galaxy, long before our time, someone or something had mastered matter to a degree we could only glimpse. Still, even among its advocates, the engineered hypothesis carried humility. It was not a claim of alien visitation, but a recognition that intelligence might leave fingerprints in the fabric of physics. If 3I-ATLAS were indeed an artifact, it would not need to be functional or alive. It could be the cosmic equivalent of a shard of glass, the surviving remnant of a technology older than our sun, wandering through space until gravity drew it into our light. In the end, no one could prove or disprove it. The evidence was too thin, the encounter too brief. But the idea lingered, reshaping the boundary between natural and artificial in cosmic thinking. It reminded scientists that engineered and natural might not be opposites at all, merely different expressions of order in the same universe. As 3I-ATLAS drifted away, fading into the dark beyond Mars's orbit, one truth remained. We had witnessed an object that behaved as if designed to endure the sun itself. Whether born of nature's laws or of intentions long forgotten, its purpose, if any, remains unknown. But its endurance whispered a quiet possibility, that somewhere in the vast silence between the stars, the act of engineering may be as ancient as the stars themselves. Every extraordinary claim demands extraordinary evidence. As soon as whispers of engineered material and plasma coherence began circulating in private research channels, the scientific community reacted with precision and skepticism. Doubt is the engine of science, and nowhere was that more evident than in the weeks following the perihelion of 3I-ATLAS. For every theory that proposed intention, structure, or intelligence, there was a carefully reasoned counterargument designed to bring the discussion back down to physics. The first counterargument was the simplest and most pragmatic: statistical inevitability. Space is enormous, and the variety of physical environments within it is beyond human imagination. Given enough time and enough material, improbable combinations will occur. Just because 3I-ATLAS looked unique did not mean it was artificial. It could simply represent a rare, naturally optimized arrangement of elements. If billions of comets exist across the galaxy, one of them was bound to display properties at the outer edge of probability. The fact that it seemed engineered, some argued, was a reflection of human pattern recognition, not evidence of design. The second counterargument focused on instrumental bias. Even though calibration tests had found no errors, skeptics warned against overconfidence in our machines. Data is never raw. It is always interpreted through the lens of algorithms and assumptions. When 3 independent spacecraft detected the same phenomenon, they were all using similar mathematical models to translate light into data. A shared computational bias, even a subtle one, could have produced a consistent illusion. We see coherence, one researcher wrote, because our instruments were built to find it. Another line of resistance emerged around comparative rarity. If 3I-ATLAS were truly composed of exotic or engineered material, where were its siblings? Why had no other interstellar object displayed similar features? The cosmos does not create single examples. Even Oumuamua and 2I Borisov, strange as they were, fit within broader statistical categories of rock and ice. A one-of-one anomaly might signal a flaw in observation, not a revolution in physics. The absence of repetition, skeptics insisted, should be treated as evidence against the extraordinary, not for it. Then came the chemical plausibility argument. The spectral lines showing nickel without iron, or light emission without mass loss, could be explained by compositional stratification. Some comets have layered surfaces, thin films of distinct materials that interact differently with radiation. A crust rich in carbonates or nitrides could theoretically create selective emission, filtering light in narrow bands. Such an effect would mimic the purity of engineered alloys without invoking intelligence. The key, skeptics said, was to resist the temptation to confuse precision with design. Nature, under the right conditions, can be as precise as any machine. A particularly elegant rebuttal came from plasma physicists, who argued that the supposed coherence of the light envelope might be the result of resonant instabilities. When an object moves through plasma at high velocity, it can set up standing waves that self-organize into symmetrical patterns. These electromagnetic bubbles could appear structured but are emergent, spontaneous order born from chaos. The universe, they reminded everyone, is full of self-organization. From spiral galaxies to soap bubbles, symmetry is not proof of design. It is a consequence of energy minimizing itself. Even the thermal resilience of 3I-ATLAS found a conservative interpretation. Some theorize that its surface could be a natural sintered crust, a dense, glass-like fusion of minerals created during prior star passes. As the object travelled through multiple systems over millions of years, repeated exposures to stellar radiation could have baked its outer layer into an insulating shell. By the time it reached our Sun, that shell might have been nearly impervious to heat. The result would look artificial, but would in fact be geological evolution on a cosmic timescale. A final counterargument touched philosophy more than physics. It warned against anthropocentric inference, the human tendency to project intention onto phenomena we cannot explain. To see design in 3I-ATLAS, critics said, was to make the same mistake ancient civilizations made when they saw gods in lightning. The object did not owe us meaning. Our search for purpose was the illusion. And yet, for all their rigour, the counterarguments had limits. They explained fragments but not the whole. Each addressed one symptom of the anomaly, the brightness, the composition, the stability, but none could connect all three in a unified natural model. The defenders of the engineered hypothesis, while cautious, noted that even skepticism must follow evidence, not comfort. To say, "we don't understand it yet" is valid, one physicist wrote, but to say, "therefore it cannot be real," is not. By late November, the scientific debate around 3I-ATLAS had crystallized into a kind of equilibrium. Movement without resolution, conviction without closure. The counter-arguments were strong, but so was the data. In that balance, science found its truest form, a conversation in motion, forever circling a mystery that refused to stand still. When 3I-ATLAS rounded the Sun and began its outbound journey, scientists expected one simple thing: for the light to fade. Every known comet follows a predictable thermal decline after perihelion. The closer it is to the Sun, the hotter it gets. The farther it moves away, the faster it cools. The relationship is so consistent that astronomers use it to confirm composition and energy output. But once again, 3I-ATLAS refused to obey the universe's usual rhythm. Its cooling curve, the gradual loss of thermal energy after exposure, did not curve at all. It flattened. At first, the data looked incomplete. The brightness of the object remained almost constant for days after its closest solar approach, even as it travelled outward at tens of kilometres per second. That defied the standard inverse square law of radiation, which dictates that intensity should drop as the square of the distance increases. By the third day, 3I-ATLAS should have dimmed by nearly half. Instead, its luminosity dipped by less than 5%. Instruments across 3 platforms, SOHO, Stereo A, and GOES 19, all recorded the same flat trend line. The object wasn't cooling, it was holding. In ordinary comets, cooling is governed by mass loss. As surface ices evaporate, they absorb latent heat, lowering the surrounding temperature. The nucleus, freed from its volatile layers, dims rapidly, but spectroscopy showed that 3I-ATLAS exhibited no new gas emissions after perihelion. Its spectral bands remained stable. No fresh hydroxyl lines, no sodium flares, no traces of sublimation. The surface appeared inert, sealed against evaporation. If it wasn't shedding heat by mass loss, then something else had to be storing or radiating it differently. One of the first theories proposed was radiative trapping. If the object was surrounded by a dense plasma envelope, photons emitted by the surface could be scattered and reabsorbed multiple times before escaping. This would create a kind of energy bottle, a slow release system in which light leaked outward gradually rather than instantly. The idea fit the data well, a smooth decay curve without sharp drops. However, modelling showed that such a mechanism would require an extremely uniform and magnetically stable field, one that persisted long after the solar wind should have dispersed. No natural comet had ever displayed such containment. Another hypothesis focused on thermal inertia. Perhaps 3I-ATLAS was made of material with an exceptionally high capacity for storing heat, something dense, conductive and crystalline. Metallic carbides or silicates could, in theory, retain warmth and release it slowly over days, but even those materials would have begun to fade faster as radiation escaped into space. Instead, infrared data from GOES 19 indicated that the object's temperature dropped only a few degrees per hour, a rate so gradual it bordered on impossible for a body of its size. The persistence of light raised another possibility: active re-emission. If the surface was photoluminescent, it could absorb invisible ultraviolet and re-emit it as visible blue light, maintaining brightness even as temperature declined. This effect would decouple thermal cooling from optical fading, explaining why the object's luminosity stayed steady while its infrared signature barely changed. Such behaviour, however, would imply a surface chemistry more advanced than anything naturally observed in interstellar material. By the fourth day, post-perihelion, the object had already travelled millions of kilometres from the Sun, yet its brightness curve remained nearly horizontal. When plotted, the data formed what scientists called the plateau, a line of stubborn constancy in a graph that should have sloped downward like a hill. Some compared it to the light curve of a powered satellite maintaining steady reflection by design. Others, more cautious, described it as the most thermally stable interstellar object ever recorded. In an internal memo, one physicist wrote, "It's as if the object learned how to cool without losing light." The phrasing was poetic but accurate. Cooling normally means fading. 3I-ATLAS managed to cool while staying luminous, separating two processes that nature usually links together. As weeks passed, the plateau finally began to decline, but not gradually. It collapsed. Around day 12, brightness fell off sharply, almost instantaneously. It was as if the system maintaining equilibrium had switched off. Some speculated that the plasma shell had dispersed, or the photonic emission mechanism had exhausted its charge. Others suggested it had finally rotated away from the line of sight, hiding its radiant face. When plotted in full, the cooling curve of 3I-ATLAS did not resemble a smooth descent but a cliff, a prolonged plateau followed by a sudden drop. It was not the cooling of an object, it was the shutdown of a process. The distinction mattered deeply. Natural bodies cool by law, engines, even broken ones, cool by design. To this day, the cooling curve remains one of the most unsettling data traces in the 3I-ATLAS record, a line that dared to stay flat against the gravity of reason and then fell all at once, as though it had decided its own moment to dim. When astronomers first examined the high-resolution coronagraph images of 3I-ATLAS, they expected the usual geometry that defines every comet near the Sun. A tail streaming away from the star, driven by solar radiation pressure and the flow of the solar wind. Instead, the images revealed something that seemed to violate the most basic rule of celestial motion: a faint linear extension of light projecting toward the Sun, not away from it. It wasn't large, but it was distinct, cutting inward like a blade of plasma. The phenomenon quickly earned a name among researchers: the anti-tail. Anti-tails have been observed before, though rarely. In most cases, they're optical illusions created by perspective. When a comet's orbital plane aligns closely with that of Earth, dust ejected weeks earlier can appear to form a line pointing sunward, even though it actually trails behind. But the geometry of 3I-ATLAS made that explanation impossible. The spacecraft watching from 3 different angles, SOHO, Stereo A and GOES 19, all saw the same structure. It was not an illusion of viewpoint. It was real, physical, and oriented directly against the expected flow of solar radiation. The first question was mechanical. How could matter be pushed toward the source of energy that should be driving it away? Radiation pressure from the sun is relentless, and even the densest dust cannot resist it. Yet the anti-tail of 3I-ATLAS held steady for nearly 6 hours, unmoving except for a faint ripple along its edge. The light within it was slightly bluer than the main envelope, implying a higher energy emission. That colour shift became the key to unlocking what might have been happening. One theory proposed a magnetic mirror effect. As the comet's plasma interacted with the sun's magnetic field lines, charged particles could have been reflected backward along converging magnetic channels, forming a filament pointing sunward. It would be similar to a solar streamer, except reversed, a temporary funnel where electric fields guided electrons inward rather than outward. This idea explained both the shape and the brightness. The line was not dust but magnetized plasma, glowing through electron excitation. A competing model suggested gravitational focusing. If the object were emitting neutral particles that later became ionized by sunlight, their initial motion could continue inward briefly before radiation pressure redirected them. During that transition, a narrow line of light could appear to point back toward the sun. The problem was timing. The observed anti-tail lasted too long for such a transient effect. Whatever sustained it had to be continuous, not momentary. Some physicists proposed an even stranger scenario, that the anti-tail wasn't a stream of particles at all, but a beam of scattered light. In this model, sunlight entered a refractive shell around the object and was redirected along the axis of rotation, producing a visible column of reflected light. If 3I-ATLAS had a crystalline or layered surface, it could act like a lens, bending photons inward. Laboratory simulations with reflective ellipsoids produce similar visual geometries, but only at micron scales. Translating that to a kilometre-wide interstellar body strained plausibility, the persistence of the structure added to the mystery. In natural comets, tails shift constantly under the influence of the solar wind. The anti-tail of 3I-ATLAS did not waver. It held alignment as though locked in place by invisible scaffolding. That rigidity suggested some kind of electromagnetic stability, a closed circuit between the object and the sun's charged environment. Plasma physicists pointed out that a moving conductor cutting through a magnetic field can generate current. If 3I-ATLAS possessed metallic composition, it might have induced a current strong enough to organize plasma around it, creating a luminous line toward the source of the magnetic field itself. Another feature deepened the puzzle. Just before the anti-tail faded, its base brightened sharply, a pulse of light that propagated outward along its axis before vanishing entirely. The event lasted less than 2 minutes but was recorded by both Stereo A and SOHO. It looked, for lack of a better term, like a discharge. No debris followed, no fragment detached. The structure simply ceased to exist, leaving the space around the object dark once more. When analysts plotted the angles, they noticed something elegant. The anti-tail was nearly collinear with the line connecting 3I-ATLAS and the centre of the sun, deviating by less than 1 degree. The precision was uncanny. Random dust outflows rarely achieve such perfect alignment. Geometry that deliberate, one researcher remarked, doesn't usually happen by chance. In the weeks that followed, scientific papers danced carefully around the term directed emission. They spoke instead of field-aligned plasma phenomena and localized photonic channeling. Yet behind the cautious language was a shared sense of awe that an interstellar object had, for a brief window, seemed to defy the most dominant force in the solar system and point back at its source. To this day, the anti-tail remains one of the most haunting images from the 3I-ATLAS encounter, a solitary line of blue-white light extending against the current of physics itself, as if the visitor had, for a few hours, turned to face the sun. By late November, as 3I-ATLAS drifted beyond the orbit of Mars, and its glare finally dimmed to the limits of the major solar observatories, the scientific conversation shifted from what had happened to what might still be happening. The interstellar visitor was fading, but it wasn't gone. If the object continued to behave in ways that defied standard thermodynamics, then the next chance to study it, the upcoming observation window, could be one of the most important campaigns in recent astronomical history. The first projections came from the Jet Propulsion Laboratory's Orbital Mechanics Group. Based on the data gathered during perihelion, 3I-ATLAS was following a hyperbolic escape trajectory, inclined about 38 degrees to the ecliptic plane. it would pass roughly 1 astronomical unit above the orbital path of Earth by early February 2026, moving outward into the region between Mars and the asteroid belt. At that distance, sunlight would be weak, and the object's brightness would fall below magnitude 21, nearly invisible to optical telescopes, but infrared and radar instruments could still track it. The challenge would be coordination. 3 facilities immediately expressed interest in the campaign. The James Webb Space Telescope, JWST, though primarily committed to deep space cosmology, retained limited discretionary time for transient targets. Its near-infrared spectrograph could detect the residual heat signature of 3I-ATLAS long after it vanished from visible wavelengths. The Goldstone Deep Space Complex planned to attempt radar reflections, mapping the object's size and rotation period with centimetre precision if signal return was possible. And the European Space Agency's Gaia extension mission, though not designed for moving objects, could refine positional data through precise parallax measurements across its wide field sensors. Together, these instruments could produce a composite portrait of the object's cooling and motion over the coming months. The strategy behind this coordinated observation was simple: to test persistence. If the object's light during perihelion was powered by temporary plasma excitation, its energy should now be gone. The infrared curve should drop smoothly as the object cooled into interstellar space. But if the brightness or heat signature stabilized, if, as some suspected, there was an ongoing internal or magnetic process, it would signal something entirely new, a sustained energy source in an unbound interstellar body. Engineers at NASA's Goddard Space Flight Center prepared a series of predictive models. One simulated radiative cooling in a high-reflectivity metallic shell, another modelled plasma decay in a weakly magnetized envelope, a third considered active luminescence, where energy stored during solar impact continued to leak as optical emission. Each produced a different light curve. The upcoming observation window would decide which, if any, matched reality. There were logistical hurdles. JWST could not pivot quickly. Every new target required reprogramming and risked disrupting its delicate thermal balance. Goldstone's radar scheduling was already booked with asteroid defense operations, yet both institutions agreed to dedicate short intervals, 10 minutes of radar time and 2 days of infrared tracking, to capture even the faintest echoes of the mysterious traveller. Ground-based telescopes also mobilized. The Very Large Telescope, VLT in Chile and Pan-STARRS in Hawaii, planned to search for faint optical reflections. If 3I-ATLAS retained its unusual albedo, it might still reflect enough sunlight to register as a faint streak against the background stars. Amateur astronomers around the world were also invited to participate through citizen science programs, submitting long exposure data in hopes of triangulating the object's fading path. What scientists hoped for was not another anomaly, but a trend, a return to predictability. If the data aligned with the expected thermal curve, it would close one of the most perplexing chapters in modern astronomy. But the unspoken tension ran deeper. If the readings deviated again, if the object glowed, pulsed, or shifted course even slightly, it would mean the mystery was not over. It would mean 3I-ATLAS had not finished speaking. Within observatories, the tone was calm but charged. Teams prepared software pipelines to capture every photon. Scripts were written to automatically alert researchers if the object brightened beyond expected margins. Even a minor flare could rewrite the story. By mid-January, the observation window will open, lasting about 40 days before the object fades permanently beyond detection. In cosmic terms, that is a heartbeat. One last chance to look before darkness claims it for good. No one can predict what the data will show. Perhaps the object will fade into silence, proving itself an odd but natural relic. Or perhaps, against all probability, it will do what it has done from the beginning: remain too bright, too calm, too deliberate for comfort. Whatever happens, the upcoming observation window will not merely test our instruments. It will test our understanding of what can survive the sun, and what, in the deep quiet of space, refuses to die. If 3I-ATLAS fades, truly fades, it will mark the end of one of the most confounding astronomical episodes in modern history. For months it has refused to follow the rules that define every natural body passing through the solar system. It glowed too brightly, cooled too slowly, and endured too much. But if the light finally dims and stays dim, if the sensors fall silent and the last photon dissipates into the cosmic background, then what remains will be not light, but interpretation, the story of what it meant while it was here. For scientists, the fading of 3I-ATLAS will be both a relief and a loss. Relief, because it restores the comfort of boundaries. A silent object can be archived. It becomes data, measurable, containable, obedient to the mathematics of closure. But loss, because the disappearance of an anomaly without explanation feels like a missed dialogue. The universe spoke in an unfamiliar language, and before we could translate it, the signal went dark. If it fades naturally, the models will find ways to claim coherence. The brightness plateau will be reclassified as delayed cooling, the blue emission as an overexcited plasma tail, the perfect orbit as coincidence. Scientific literature will absorb the strangeness and smooth it into the continuum of known behaviour. In a few years, the event will sit quietly in textbooks, under headings like anomalous perihelion brightening or interstellar object thermal deviation. The edges will be softened, the astonishment replaced by footnotes. That is how science digests mystery, by classifying it until it no longer feels like one. But there will always be the data that does not fit, the line in the spectrum that should not exist, the symmetry that defies chaos, the silence of acceleration. The researchers who spent long nights staring at those graphs will remember what it felt like when logic bent under the weight of observation. For them, the fading won't feel like resolution. It will feel like an unanswered question drifting beyond reach. Philosophers of science often say that fading is how the cosmos maintains its dignity. It never allows us to stare too long. Every object that astonishes us eventually slips away, leaving behind the humility that drives inquiry. Galileo watched stars vanish at dawn. Voyager will fade beyond signal range. 3I-ATLAS, if it dims completely, will join that lineage of unreachable wonders. It will be proof that the universe still keeps secrets, not out of malice, but out of scale. For a few, the fading will carry a more poetic weight. They will wonder whether the light of 3I-ATLAS was ever meant to last. Perhaps its brilliance was not defiance, but farewell. The flare of a traveller burning the last of its stored energy before returning to the cold interstellar dark. In that sense, fading is not an ending, but a return to origin. The cosmos is full of such quiet departures. Stars flare and collapse, comets bloom and vanish, signals peak and dissolve. The story repeats, but each time it takes something of us with it, the hunger to know what cannot yet be known. There will be no ceremony when the instruments stop detecting it. A few observatories will issue final logs, noting a decline below the threshold of measurable flux. The file will close with coordinates and timestamps, not emotion. And yet, in the silence that follows, there will be a feeling, the same one that accompanies the end of a conversation you didn't realize mattered until it stopped. If it fades, it will mean that 3I-ATLAS was, after all, mortal, governed by physics not defiant of it. But it will also mean that for a brief moment, humanity encountered something that tested the limits of its certainty. It arrived uninvited, illuminated the sky with impossible precision, and then left, taking its reason with it. And if, somewhere in the frozen dark beyond Mars, that last shimmer finally dies, its legacy will not be light but perspective, a reminder that the universe is still capable of surprise, and that every glow, no matter how inexplicable, carries within it the promise of a greater silence waiting to be understood. If 3I-ATLAS holds, if the light does not fade, if the object continues to burn softly in defiance of distance and cold, then the quiet boundaries of astrophysics will begin to tremble. For centuries, humanity has trusted that the universe runs on decay. Heat radiates, energy disperses, light dies. That rhythm of loss defines everything from a candle to a star. But if 3I-ATLAS refuses to dim as it drifts farther from the sun, then something in that rhythm is broken or rewritten. The first confirmation would come quietly. A late-night observer at Goldstone or JWST would notice that the infrared trace, expected to flatten into noise, had stabilized instead. A team at the European Southern Observatory would double-check the magnitude logs and find, to their disbelief, that brightness had actually increased by a fraction of a percent. Within hours, the data pipelines would light up. Observatories across the world, ground, orbital, and deep space, would redirect their instruments. The object that should have gone dark would suddenly become the most observed speck of matter in the solar system. If it holds, the first explanations will reach for safety. Perhaps its reflection, sunlight bouncing off a distant, unseen dust cloud. Perhaps the sensors are detecting an artifact, or the angle of observation has changed. But as the weeks pass and the readings remain unchanged, that caution will turn into unease. The consensus that brightness means energy will still apply, and yet the source will remain invisible. 3I-ATLAS will be glowing in a way that implies internal stability, an energy source self-contained, independent of the sun. That possibility alone would rewrite half of thermodynamics. Objects in space are supposed to cool exponentially after a solar encounter. They radiate until equilibrium, then drift as frozen rock. But a sustained emission far beyond the reach of solar heat implies either continuous energy generation or an unknown interaction with the interstellar medium. It would mean that 3I-ATLAS is not merely reflecting light, it is producing it. The implications ripple outward like gravity itself. Could the object contain trapped plasma fields, still oscillating from its encounter with the sun? Could it be using electromagnetic resonance to maintain energy balance? Or, the question that will linger in whispers rather than in papers, could it be something made to hold? A structure, not a stone. A system, not a remnant. Engineers studying the light signature would begin comparing it to known human technologies, persistent emission devices, photonic storage materials, superconductive resonators. Nothing would match, and yet everything would feel familiar, a geometry of control written into nature. The idea that an interstellar object could sustain luminosity through active regulation rather than passive reflection would collapse the distinction between artifact and asteroid. The term engineered hypothesis would return to the headlines, this time without irony. The public reaction would be immediate. News outlets would call it the light that refuses to die. Social media would swarm with theories, alien probes, cosmic beacons, even metaphors for resilience. Religious groups would find in it a kind of confirmation, a celestial ember that endures in defiance of entropy. Meanwhile, scientists would do what they always do: measure, compare, and try to keep wonder from sounding like belief. If it holds, time itself will become a variable. The longer the glow persists, the more pressure builds to understand it. At a week it's an anomaly, at a month it's a mystery, at a year it's a paradigm shift. Instruments will be recalibrated, theories rewritten, textbooks updated not to explain the impossible, but to accommodate it. And somewhere deep within a laboratory, someone will whisper what no one wants to print, that perhaps this is not an object at all, but a process, a living equation still unfolding. If it holds, it will force a change in how we define death in physics. Because to hold light when it should have gone out is to resist entropy, the single law that has never been broken. Whether through plasma resonance, unknown matter, or deliberate architecture, 3I-ATLAS would stand as our proof that the universe still hides technologies of endurance beyond our comprehension. And if, months from now, the glow remains steady, if the instruments confirm that the light of 3I-ATLAS is neither reflection nor illusion, then we will know that something out there has found a way to live forever in the cold. It will not be loud or apocalyptic. It will simply be a quiet, unwavering ember in the dark, rewriting what it means for something to survive the sun. When 3I-ATLAS first entered the solar system, it arrived without announcement, without trajectory in our databases, without even a name. It was simply a new point of light, one more visitor in a sky already full of them. Yet what followed transformed it from a data point into a teacher. It broke predictions, challenged instruments, and dismantled the assumption that the laws of nature are always tidy. Whether it was a comet, a fragment, or something we still have no language for, 3I-ATLAS left behind more than questions. It left lessons, quiet, humbling reminders of how fragile our certainty really is. The first lesson is that observation is not ownership. We often assume that by measuring we understand, that data implies control, but 3I-ATLAS exposed the gap between detection and comprehension. We measured its brightness, its orbit, its heat, and still it slipped through our equations like sand through fingers. It reminded the scientific world that to observe the universe is to participate in something far larger than our instruments. The cosmos does not answer to curiosity. It merely allows us to listen, briefly, before the signal fades. The second lesson lies in humility before anomalies. For centuries, Each generation of scientists has faced an event that refused explanation. Comets that defied gravitational models, stars that dimmed for reasons unknown, radiation that appeared where no source existed. In every era, such anomalies felt like threats to reason, yet in hindsight they became the catalysts of progress. X-rays, radio waves, and dark matter all began as impossible observations. 3I-ATLAS joins that lineage. Its contradictions are not failures of understanding, but invitations to expand what understanding means. The third lesson is about silence, the kind that follows every discovery too vast to interpret. When the data from 3I-ATLAS first arrived, the noise of speculation was deafening. Plasma fields, engineered material, living artifact. But as months passed, and the light either faded or held, something shifted. Scientists stopped speaking with certainty. They began to listen instead, not for answers, but for patterns in the quiet. The universe does not need our approval to be strange. Silence, in the end, is the most honest form of respect a scientist can offer to the unknown. There is also a lesson in continuity. The story of 3I-ATLAS is not isolated. It connects to Oumuamua, to 2I Borisov, and to every unidentified fragment that has ever crossed our skies. Each object expands the conversation about what exists beyond our solar neighbourhood. Some follow predictable paths, others rewrite the map entirely. Together they form a kind of cosmic syllabus, chapters in a course we didn't realise we were taking, where every anomaly becomes a lecture on humility, probability, and the limits of perception. Yet perhaps the deepest lesson is philosophical, that ignorance is not failure, it is fuel. Humanity's strength has never been in what it knows, but in its refusal to stop asking. 3I-ATLAS forced us to confront a scenario with no precedent, no comforting analogies, no ready-made labels. In that discomfort, it reignited something ancient, wonder. The same emotion that drove our ancestors to chart the stars now drives us to decode data from space. Wonder is not childish, it is the engine of civilization. If the object fades, we will learn that some mysteries end in silence. If it holds, we will learn that the universe still harbours endurance beyond entropy. Either way, the lesson is the same. The cosmos remains larger than comprehension, and our role within it is not to dominate, but to witness. In laboratories and observatories, people will continue to model, to simulate, to question. Not because they expect to solve 3I-ATLAS, but because they cannot ignore it. The object's legacy will not be in what it was, but in what it forced us to become. A species reminded that certainty is temporary, curiosity eternal, and that sometimes the greatest progress comes not from answers, but from standing before the unknown and daring to call it beautiful. Every mystery, no matter how vast, eventually reaches its moment of reckoning, the point where speculation must give way to observation. For 3I-ATLAS, that moment is approaching fast. The object that once glowed brighter than theory allowed is now receding into the cold, with only a few short weeks left before it slips beyond the range of our best instruments. Scientists call it the countdown to clarity, the final observation window before distance and silence reclaim the interstellar visitor. Yet clarity, in this case, may not mean understanding. It may simply mean learning what we are not ready to know. The countdown began when the light curve of 3I-ATLAS stabilized against all expectations. It neither faded as a dying comet nor brightened as an active emitter. It held steady and calm as if conserving some deep equilibrium. The orbital projections suggest that by mid-February 2026, it will pass beyond the reach of radar tracking and vanish from the field of every major telescope. Between now and then lies a narrow corridor of opportunity, a final 40 days of observation, during which science must decide what the object truly is, or admit that it cannot. Inside mission control rooms, the atmosphere is both methodical and electric. Every hour of telescope time counts. The James Webb Space Telescope will aim its infrared sensors at the coordinates, searching for thermal echoes from the object's surface. Goldstone's radar arrays will send one last pulse, hoping for a reflection sharp enough to map contours and spin. The European Space Agency's Gaia extension will refine trajectory data, tracking whether the path of 3I-ATLAS still matches Newtonian prediction, or if, impossibly, some hidden force continues to guide it. Each of these instruments represents a fragment of clarity, a single lens through which the universe may choose to speak one last time. For the scientists involved, the countdown is more than a technical deadline. It's an emotional one. Years of debate have produced two incompatible narratives. One describes a natural object behaving at the extreme edge of physics, a relic of cosmic chemistry beyond our experience. The other whispers of structure, design, or purpose, not proof of intelligence, but evidence that matter itself may remember how to organize beyond our comprehension. The data from this final campaign will either quiet those whispers or amplify them beyond recall. If the brightness continues unchanged, it will be the first time in recorded history that an unbound interstellar object maintained a mission independent of solar input. That single fact would force revisions across disciplines: thermodynamics, plasma physics, and material science. If, on the other hand, the glow fades in a smooth, predictable curve, the tension will break like a long-held breath. Scientists will return to familiar language: cooling, dispersion, equilibrium. The event will be written off as extreme but natural. The world will move on, and the mystery will retreat into data archives. Yet many quietly suspect that 3I-ATLAS will not cooperate. It has defied too many expectations already. Its light has a rhythm that feels less like decay and more like persistence, the faint, stubborn heartbeat of a system not yet finished. And so the countdown is not only to clarity, but to confrontation, between the universe we think we understand and the one that continues to surprise us. Outside the laboratories, the public watches too. News tickers trace the object's dwindling brightness like an interstellar pulse. Commentators speak of it as a symbol of endurance, of mystery, of humility. But within the observatories, the sentiment is quieter, almost reverent. Each photon that reaches Earth is a message from something ancient, something that may never pass this way again. When the countdown ends, clarity may not come in the form of revelation. It may arrive instead as acceptance, that 3I-ATLAS, whether natural or designed, reminded us of the oldest truth in science, that knowing has limits, but looking does not. The final images will not close the story. They will only freeze a moment in time, the last recorded shimmer of a traveller that came from the dark, met the sun, and left us with questions bright enough to outlive its light.